In the shadows of Geneva, beneath the world floor, lies a marvel of human ingenuity and a likely harbinger of doom. The beast known as the Large Hadron Collider, LHC. It is a miracle of intelligent evaluation that allows analysts to destroy subatomic particles and prompt the discovery of the strange God particle, the Higgs boson. So far, the famous physicist Brian Cox has made a chilling statement that has sent buzzes through the philosophy community. Something remarkable has been studied at CERN, which may have consequences beyond our understanding. Has our central goal of developing education led us down the path of disaster, forcing us to jump into the pit of this obvious problem? Before exploring the implications of Cox's explanation, it is important to understand what the Large Hadron Collider, LHC, used by CERN is. The LHC, a 27 kilometers long ring of superconducting magnets, is the world's most powerful nuclear smasher. It remains the pinnacle of human achievement, capable of reproducing the conditions that created the universe. This gigantic design allows us to unlock the secrets of the universe and reveal something perhaps more important and perhaps more disturbing. CERN, founded in 1954, is one of the most prestigious scientific organizations in the world, with the participation of 23 countries and a huge number of experts. It serves as a center for collaboration and progress. The LHC is a central project at CERN, but it is only one part of a vast network of accelerators and detectors that probe the subatomic world. The LHC accelerates protons to almost the speed of light, recreating the energy of the universe during the Big Bang. The subsequent collisions increase the temperature millions of times compared to the core of the Sun. An advanced magnetic device directs the protons, while state-of-the-art cooling systems keep the magnets at cooler than room temperatures. The design of the LHC is a technological marvel. It works deep underground, shielded from cosmic radiation. The entire circuit is cooled to a temperature colder than the vacuum of space, which is necessary for the operation of superconducting magnets. Collisions occur at 4 points on the petal ring, each corresponding to one of the 4 main particle detectors: Atlas, CMS, ALICE, and LHCb. These finders capture the aftermath of crashes, allowing scientists to sift through the debris for the elusive Higgs boson, which is crucial to deciphering the structure of the universe. This process is similar to putting together a cosmic puzzle, where each piece provides insight into the nature of the universe. The LHC is not just a scientific tool. It is an act of human creativity and ambition. It symbolizes our search for knowledge and our desire to understand the fundamental forces that shape our universe. However, crossing the limits of our understanding, we must also consider the arising ethical and existential questions. What are the risks of exploring the unknown? Could our search for information accidentally trigger forces unknown to us? In the sanitized halls of CERN, where the limits of human understanding are constantly expanding, a discovery was made that sent the backs of even the most experienced scientists down the shutters. Brian Cox, a former CERN scientist and respected voice in the field of particle physics, recently made a statement that intrigued established scientists. CERN's Large Hadron Collider aims to create a miniature version of the Big Bang, the event that gave birth to our universe. Cox also highlighted the potential implications of that goal, noting the LHC's unique ability to create new anomalies, including the ability to unlock the secrets of the Higgs boson and study dark matter, the substance that makes up much of the universe. The possibility of a little Big Bang is not just a theoretical concept. This is a tangible reality at the LHC. The conditions inside the collider mimic the conditions that existed at the beginning of the universe, allowing scientists to witness the birth of existence. However, with such power comes great responsibility and potential risks. Consider a scenario where something goes catastrophically wrong. In 1978, the Russian physicist Anatoly Bugorsk had an accident at the Institute of High-Energy Physics in Protvino, Russia. The malfunction caused his head to be sliced open by a proton beam, resulting in serious injuries. Despite this, Bugorsky persisted and continued his work, emphasizing the enormous power and potential dangers of particle accelerators. The risks associated with a nuclear reactor like the LHC should not be taken lightly. The possibility of unexpected reactions and the manipulation of the fabric of reality is not science fiction, but some real concerns expressed by well-known scientists. One of the major fears surrounding the LHC experiments is the possibility of creating miniature black holes. These pockets of space-time have such strong gravitational forces that even light cannot escape. If the LHC creates even a small amount of such matter, it could potentially begin to consume the Earth from within. However, CERN scientists assured the public that the resulting black holes are transient and disappear in an instant. Understanding how the LHC can create a black hole involves the basic mechanics of particle accelerators. When protons collide at nearly the speed of light, the energy is powerful enough to warp the fabric of space-time itself. Imagine a trampoline stretched taut and a heavy weight dropped on it. The surface will deform, and if the weight is significant enough, it can create a void. This analogy helps illustrate the potential of the LHC to create a gravitational anomaly. This interesting but terrifying possibility has even attracted the attention of respected physicists such as the late Stephen Hawking. In his writings, Hawking warned that the Higgs boson could become unstable at very high energy levels, causing a potentially catastrophic vacuum decay that could destroy the universe. Respected cosmologist Sir Martin Rees has also raised concerns about particle accelerator tests, including those at CERN. In his book on future risks to humanity, he revisited the possible dangers of nuclear fission experiments, which include creating vacuum instability. This instability could theoretically trigger a phase change that would reverberate through space-time and cause a catastrophe of colossal proportions. While these scenarios are still highly theoretical, even the slightest possibility should give us pause for thought. The stakes are very high and the margin for error small. CERN scientists have carefully assessed the potential risks associated with these experiments. They implemented several safety protocols and precautions to mitigate potential hazards. However, there is a degree of uncertainty associated with scientific research, especially when entering uncharted territory. The pursuit of knowledge has always been associated with risk, but it is this desire to push the boundaries that has driven human evolution. The LHC is the culmination of decades of scientific development and international cooperation. But beneath this impressive exterior lies a field of rigorous research full of potential risks and ethical considerations. The collider's main goal of unraveling the mysteries of particle physics has led to amazing discoveries, including the elusive Higgs boson. But the enormous energy generated within its borders also raises concerns about the potentially catastrophic consequences of such an effort. While extensive safety measures exist to mitigate the risks, the possibility of catastrophic events such as the creation of microscopic black holes or other unexpected anomalies cannot be completely ignored. If scientists are to push the boundaries of our understanding, it is important that they do so with an awareness of the potential consequences and a commitment to openness and public debate. As we delve deeper into CERN's Large Hadron Collider and the scientific endeavors associated with it, it becomes increasingly clear that the pursuit of knowledge is not without risk and uncertainty.
The LHC, with its unparalleled capabilities and remarkable discoveries, is a testament to man's creativity and relentless quest to understand the fundamental laws of the universe. But beneath this shiny exterior lies considerable scientific research, fraught with potential dangers and ethical considerations. Experiments conducted within the vast infrastructure of Tormame use energies and forces beyond the comprehension of most laymen. The collision of subatomic particles at nearly the speed of light creates conditions similar to those that existed in the first moments of the universe, allowing scientists to study the basic building blocks of matter and probe spacetime. But the enormous energies associated with these collisions also pose serious risks, known and unknown. One of the most pressing problems with the operation of the Large Hadron Collider is the creation of microscopic black holes or other exotic phenomena, which can have unexpected consequences. Although theoretical calculations suggest that such black holes would be short-lived and pose no threat to Earth or its inhabitants, the possibility of accidentally releasing forces beyond our control remains a disturbing possibility. In addition, the sheer scale and complexity of crash testing requires careful safety protocols and strict controls to minimize potential risks. The global community of scientists and researchers involved in the work on HAL is very aware of the need to prioritize safety and ensure that all experiments are conducted with the utmost care and responsibility. The Large Hadron Collider, LHC, of CERN is a monumental scientific effort that represents the pinnacle of particle physics and cosmology. Located near Geneva, Switzerland, the underground LHC is a 27 kilometers ring of superconducting magnets designed to accelerate protons and other particles to nearly the speed of light. At such extreme speeds, these particles are then caused to collide, recreating the conditions that existed immediately after the Big Bang. These collisions generate energies millions of times hotter than the core of the Sun, allowing scientists to study the basic building blocks of matter and the forces that govern the universe. One of the most important achievements of the LHC was the discovery of the Higgs boson in 2012. This elusive particle, predicted by the Standard Model of particle physics, plays a crucial role in giving mass to other particles by interacting with the Higgs field. The confirmation of the existence of the Higgs boson confirmed decades of theoretical work and experimental work, strengthening our understanding of the fundamental forces of nature.